How skyscrapers touch the sky. Imagine that you and thousands of other people decide to build the tallest tower the world has ever seen. Not 10 stories, not 100 stories. You wanted to build a tower that reaches the heavens. What would you need? A mountain of bricks? Millions of tons of steel? A gigantic foundation? And what would happen when the wind started pushing on it? Today we're going to travel from an ancient story to one of the most fascinating fields of engineering, structural engineering. Because when humans build upward, we're really asking a very difficult question. How do you make something enormous stay standing? Let's start with an ancient story, the Tower of Babel. According to the biblical story in Genesis, people gathered together and decided to build a city with a tower that would reach toward the heavens. They had bricks, they had materials, they had the technology of their time, and they had a very ambitious goal: build upward. But the story takes a surprising turn. Their languages become confused, they can no longer understand one another, and the construction stops. The story is about human ambition, communication, and the limits of what people can accomplish together. But let's imagine something different. Suppose the builders had perfect communication. Suppose they had unlimited workers. And suppose they had modern engineering. Could we actually build a tower that enormous? Well, we can certainly build extremely tall buildings. But there is a reason we don't simply keep adding floors forever. And the reason is not just money, it is physics. Humans have been building higher and higher. For most of human history, buildings were relatively short. Stone temples, castles, churches, and other monumental structures could become surprisingly tall. But there was a fundamental problem. The higher you build, the more material you need to support everything above it. Imagine putting one book on the floor. No problem. Now put another book on top. Still easy. Add 10 more. Still fine. But imagine stacking thousands of books into a tower. The books at the bottom have to support the weight of every book above them. A building has the same problem. Except a building isn't made of a few thousand books. It can contain millions of tons of material. And every kilogram of that material has to be supported. So engineers face a strange problem. The building has to be strong enough to hold itself up, while also being light enough that it doesn't become ridiculously heavy. Let's introduce the world's tallest building. Today, one building stands far above most of the world's skyscrapers, the Burj Khalifa in Dubai. It rises about 828 meters, or more than half a mile, from the ground to its highest architectural point. That's more than 160 stories. Imagine standing at the bottom and looking straight up. The people at the top aren't just high above the ground. They're living and working inside a gigantic engineering experiment involving gravity, wind, steel, concrete, vibrations, temperature, elevators, and foundations. And here's the amazing part. The building doesn't simply stand there because someone made its walls really strong. Its entire shape is designed to work with the forces acting on it. That is the key idea of structural engineering. Let's start with the force you already know: gravity. Gravity pulls everything toward Earth. You, me, a pencil, a car, and a skyscraper. A building has to carry its own weight, but it also has to carry everything inside it: people, furniture, computers, water, air conditioning equipment, sometimes even swimming pools. So engineers ask, where does all that weight go? The answer is a pathway called a load path. Imagine standing on a bridge. Your weight pushes down on the bridge. The bridge transfers that force through its structural members. Those members transfer the force into the supports. The supports transfer it into the foundations. And the foundations transfer it into the ground. A skyscraper works in a similar way. From floor to beams, columns, and structural walls, to foundation, and finally ground. The force has to travel somewhere. If you interrupt that pathway, you can create a serious structural problem. So can the foundation carry everything? Now imagine building a skyscraper. You make it 10 stories tall. No problem. Then 50 stories. Then 100. Then 200. Every additional floor adds weight. And that weight eventually reaches the foundation. So you might think, easy. Just make the foundation bigger. And engineers actually do something like that. Tall buildings can have enormous foundations extending deep into the ground. Some use huge reinforced concrete foundation systems and deep piles that transfer loads into stronger layers of soil or rock. But here's the catch. The ground itself has limits. If you put too much load onto weak soil, the soil can deform. The building might settle. And if different parts of the building settle by different amounts, the structure can become distorted. So engineers have to understand not only the building, but also the earth underneath it. This is where structural engineering meets geotechnical engineering. The skyscraper doesn't end at ground level. Its engineering continues deep underground. But gravity isn't the only problem. Now let's make the building taller. Much taller. Suddenly another force becomes extremely important. Wind. You may have noticed something strange on a windy day. A short building might barely seem affected. But imagine holding a tall, thin piece of cardboard in the wind. It bends. Why? Because the wind is pushing against a large surface. And the taller the building becomes, the more important wind can become. A skyscraper is essentially a gigantic object sticking into the atmosphere. Wind pushes on it. And the building responds by moving. Yes, a skyscraper can actually sway. Wait, skyscrapers move? You might think a skyscraper shouldn't move. But that's not quite right. A skyscraper that never moved at all would be extremely difficult to design. Instead, engineers design buildings that can move safely. Think about a tall tree. When the wind blows, the tree bends and sways. It doesn't need to be perfectly rigid. A skyscraper can behave somewhat similarly. The goal isn't don't move. The goal is move in a controlled way. Engineers calculate how much the building might move and how people inside will experience that motion. Because there's another problem. Even if a building is structurally safe, people don't want to feel like they're standing on a boat. So engineers care about both. Will the building remain safe? And will people feel comfortable inside it? Those are related, but not exactly the same question. Why don't skyscrapers just bend over? Here's another fascinating problem. Imagine taking a long, thin ruler. Hold it vertically. Now push gently on the top. It bends. Push harder, and it may suddenly buckle sideways. This phenomenon is called buckling, and it becomes very important when structures are tall and slender. A structural column isn't simply being asked to hold weight. It may also have to resist bending and buckling. This creates an important engineering trade-off. Tall and slender looks elegant, but tall and slender can be structurally challenging. That's one reason skyscrapers aren't simply enormous vertical walls. Their geometry matters a lot. Why do tall buildings have strange shapes? Look at some of the world's tallest skyscrapers. Many don't look like simple rectangular boxes. They may taper, they may have setbacks, they may twist, they may have different sections arranged around a central core. Why? Because shape can help control forces. Imagine blowing air toward a giant rectangular box. The wind hits the flat surface. But if the building becomes narrower as it rises, the airflow can behave differently. Some skyscrapers are deliberately shaped so that wind cannot push the entire building in one simple, repetitive rhythm. In other words, the shape of a skyscraper is part of its structural system. Architecture isn't just about making a building beautiful. Sometimes the shape is helping the building survive. Now let's talk about materials. Two of the most important materials in modern skyscraper construction are steel and concrete. Steel is extremely strong and can carry large loads. But concrete has enormous advantages too. Concrete is very strong when compressed. And that's useful because many parts of a building experience compression. Engineers can also combine concrete with steel reinforcement. That's called reinforced concrete. The two materials work together. But there's a catch. Materials are heavy. And that takes us back to our original problem. If you make a building stronger by simply adding more and more material, you make it heavier. And now that extra weight has to be supported, so you need even more structure, which adds even more weight. You can see the problem. It's a little like trying to make a backpack stronger by adding more metal to it. Eventually, the backpack becomes so heavy that the stronger straps have to carry the weight of the backpack itself. So structural engineers are constantly searching for something very clever. Use exactly the material you need in exactly the places where it helps most. Is there a maximum height? So now we can return to our original question. Why don't we just build a building 2 kilometers tall? Or 5 kilometers? Or 10 kilometers. There isn't one simple number called the maximum possible building height. Instead, many different problems become increasingly difficult as a building gets taller. Gravity becomes more demanding. The structure becomes heavier. The foundation becomes more challenging. Wind becomes more important. The building may sway more. Elevators become more complicated. Materials and construction become more difficult. And of course, there is the question, is anyone willing to pay for it? Engineering isn't just about what is physically possible. It's also about what is practical. Could we build something taller than the Burj Khalifa? Probably. Humans have already proposed buildings significantly taller than the Burj Khalifa. Engineers can design structures that push beyond today's height records. But here's the important lesson. Breaking a height record isn't simply a matter of saying, let's add another 100 floors. Every additional meter changes the engineering problem. The building becomes a different creature. The forces change. The structure changes. The construction changes. The transportation system changes. Even the people inside the building experience different conditions. At some point, the question changes from, can we build it, to, should we build it? And now let's return to the Tower of Babel. The ancient builders wanted to reach the heavens. Modern engineers have actually come surprisingly close to that dream. We can build structures hundreds of meters into the sky. We can make buildings that survive enormous forces. We can drill foundations deep into the earth. We can calculate how structures respond to wind. We can design materials at microscopic scales. And we can simulate an entire building on a computer before construction even begins. But there's something the ancient story gets wonderfully right. Building something enormous isn't just about having enough bricks. You need people to communicate. You need different kinds of knowledge. You need architects, structural engineers, geotechnical engineers, mechanical engineers, electrical engineers, construction workers, surveyors, scientists, and thousands of other people. A skyscraper is not one giant object. It is a giant system. So the next time you look at a skyscraper, don't just look at how tall it is. Look at it differently. Ask yourself, where is the weight going? What is carrying the floors? Where does the load enter the ground? How does the building resist the wind? Why is it shaped that way? What would happen if the building were twice as tall? Those are the kinds of questions structural engineers ask, and perhaps that's the most interesting connection between an ancient tower and a modern skyscraper. The Tower of Babel asks, how high can humans build? Structural engineering asks a more useful question. What forces are trying to bring it down, and how can we design around them? Because every skyscraper is having a conversation with gravity. Every tall building is negotiating with the wind. And every foundation is asking the earth, can you carry this? That is the hidden science inside every tower. The taller we build, the more carefully we have to understand the forces beneath our feet and above our heads. Engineering the future together.